Now, actually, electricity can be quite difficult to understand. We use it all the time. Every time we flick a switch, or we're using our phones or other devices, we're using electrical energy. But what it actually is quite a difficult concept because we can't see it. And Benjamin Franklin, President of the United States, part-time physicist, was one of the important players in our understanding of electricity. He famously, I don't know if you were taught this in high school, but flew a kite in a thunderstorm with a key on a string, because he thought that that lightning was electrical energy, and he was right. And his key got zapped, and he didn't die. But that was more luck than good management. So he was helping us in our understanding of electricity. So we've got this part, electric, which is very similar to electron, isn't it? And what Benjamin Franklin didn't know, because we didn't know the structure of the atom at this time, was that it's the electrons that flow through our metals. So if I have a copper wire here, and I'm just going to put 1 plus on here, even though my copper would probably be 2 plus, mostly. And they are my delocalized valence electrons that are able to move in our metals. We know this is a property of metals. So if I say this is a copper wire, and if I hook this up to a power supply, and what I'm drawing at the moment is actually a representation of a circuit similar to what's on page 31. This represents a battery, and the long stick is the positive end, and the short stick is negative terminals. If you've looked at a battery, or a cell, you would know that they're marked plus and minus, aren't they? So that you stick them in the correct way around. This is a battery because I've done that twice. And if we think about a car battery, it's actually 6 cells. So this represents a cell. Americans call their mobile phones cell phones. Yeah, and they're right. They have a cell. They don't have a battery in their phone, because a battery is a series of cells. So this is words that might help in the context of the question. We don't go into, you won't ever have to define a battery as a series of cells. And if you use the terms incorrectly and call the battery a cell or a cell a battery, you won't be penalised, but it doesn't hurt you to know that they are actually different things. So this then has a positive charge, or that's the positively charged end, and that's the negatively charged end. And our battery is our power source, if you like. This is our source of energy. And if it's a battery, it would actually be chemical energy. And when we have our circuit operating, our chemical energy transformed into other kind of energy. If it's for a light, then the light is turned on, the chemical energy is transformed into light energy. If it was your mobile phone, then that chemical energy is going to be transformed into sound and light energy. And if it, if it was a heater or something like that, then it's going to turn into heat, etc. So here, for our battery, it's going to be chemical energy, and it's transformed into whatever we're using this circuit to do for us. Now, when Benjamin Franklin realised it was a movement of charge, and he didn't know about the structure of the atom because that hadn't been discovered yet, he had to decide which charge was moving, and he chose positive. And he was wrong, because it's actually the negative charge, the electrons, that move. And so in physics, we call the movement of the charge current. And so, if I were to put on here the direction that my electrons are going to move, which is the actual motion of the actual charge carriers, they would be repelled from the negative terminal and attracted towards the positive terminal, because like charges repel and opposite charges attract. So my electrons actually travel in this direction.
So does the negative end of, well, negative part of the cell ever go on the left side, or it's always in a positive or
it
negative?
doesn't matter which orientation you draw it.
Okay.
Yeah, you can draw your power source around the other way.
Yeah.
That's fine. The thing, I guess, is to make sure that you get your directions right. So if my electrons are travelling in that direction, and that is the actual direction of the travel of our negative charges, if I focused in on just a little section like I've got here, and I couldn't tell where the beginning and end of this section were, and the electrons were moving that way, it could look like the positive particles are moving in the opposite direction. Okay, so that means that my current, which represents the movement of positive charges in the opposite direction, it has to be away from the positive terminal and towards the negative terminal. But current, like I said, it's based on a mistake to have it going in that direction, but there are good reasons to keep it because it helps with other aspects of physics to keep this this definition of current. This is a circuit I've drawn. It's actually a short circuit because I didn't put anything in there to use the energy. So I might put in a light bulb here, and I'm going to put in an old-fashioned sort of light bulb. This is called an incandescent. And the way they would work is this tiny, very thin piece of wire, which is called the filament, would actually have a high resistance to electrical charge and get white hot. And that is where the light would come from, is from making this filament, which was made out of metal glow white hot. And the glass bit over the top is to protect you from it, so that one, you don't get electrocuted when you if you touch the bare wire, which is a good reason to have the glass there. But it could also prevent the filament from breaking, and this would tend to get, the glass gets really hot too. If you had an old style incandescent bulb and the wire broke, so the bulb stopped working, so you want to replace it, you want to take it out and put in a new one, you'd have to either wait for it to cool down or grab it with a cloth or something like that, because they would get very hot. Halogen bulbs get very hot as well. More and more our lighting is, these are fluorescent, I reckon, either fluorescent or LEDs. We don't talk about the electricity, what a light emitting diode means in this course, but some of you might know. Basically, with a diode, it'll only work if the electricity is flowing through it in a particular direction. So it will work in one direction and it won't work in the other. But we don't have to worry about diodes. We use metal wires because why? Good conductors. Yes, they're the ones that have those delocalized valence electrons that are free to move, and so they're often used in electric circuits. Do you know which metal is the best conductor?
Is it copper?
It's not copper. It's actually silver. Why do you reckon we don't wire our houses up with silver when it's the best conductor?
Expensive.
Yeah.
Yeah. So it's a cost trade-off here. Copper is still a very good conductor, and it's cheap, because what drives the cost of our raw materials? Abundance. Yeah. So there's a lot more copper, and so it's cheaper than silver, and so we wire our houses with copper, and actually the high tension wires use aluminium.
If you were to use silver, would it have any advantage? Like if you were to wire a whole house with silver, could you do things that you can't with copper, or is it sort of just much of a muchness?
Yeah, it's not going to change your experience of the house, for sure. What happens, the better conductors aren't going to have as much energy loss to heat. Because if you think about, we've still got things moving, we still have electrons moving, and so wherever we have motion, we have heat. But the more freely they move, the less heat they're going to generate. And so our wires in our houses hopefully aren't in a condition where they're going to get hot. But if you've ever looked at a power bill from at home, it will talk to you about line losses as well. How much electricity is lost between the generator, the dam, the hydro scheme, and all the way to your house. So they make way more electricity than actually reaches people's houses because it's lost along the lines. It doesn't have to be a lot of heat lost, but if you've got hundreds of kilometres of lines, then a little losses per metre is going to add up. The other thing to think about though here is that the motion of the electrons, it's not like that we've got to have all these electrons whizzing around. What we have is motion, and so the one electron moving in that direction there, and then the one electron moving there, they're all moving around just like, if we had a whole heap of marbles on the track, and we're just moving them, and whatever they're moving, there's current. So there's nothing special about the electrons here, just like there's nothing special about the electrons anywhere in the circuit. It's just them all moving.
Do they travel through the battery?
They do. And basically, if they get back, as far as their ability to do work is concerned, we'll get to that later, but they need another push. Another name for, well, we do need to think about what's happening in the battery. Just say it's a 6-volt battery. Or a 12-volt battery, it doesn't really matter. We can think about the using of the energy in the circuit is, so my light bulb here. If I started out at 6 volts here, I end up using up all my volts across my light bulb there, say, in this circuit. However, whatever kind of drain there is from the battery, from the light bulb, it's going to lose that energy. You could think of it as like water over a waterfall. Okay, so we've got this stored up energy in the water in the waterfall at the top. And then the water falls down, it crashes down over the waterfall, so that energy is used in that motion. And then down the bottom, the water's pretty calm, and it hasn't got that same energy as it had at the top. That's what's happening when we're using our energy. But if we go back through the battery here, or if we're thinking of we've gone around, then we're giving them that energy back again. That's what we're using, is that energy from the battery. Does that sort of, like, we will go over this more and more over the next couple of weeks. It can also be called, like, this is an incorrect name. So it can have, like, it will have volts. And I'm sure you've all read that on your, like a AAA, 1.5 volts or whatever, tells you how much energy, how much work you can do from that cell. But it's also called electromotive force, which is an incorrect name, but it can help you with the concept that the battery is pushing the electrons. Without the battery in this circuit, nothing happens. Okay, the electrons won't move by themselves. We need to have something that will push them. And that is what our power source is doing here for us, is it's pushing the battery, pushing the electrons. Now, this is, like I said, this is a circuit, and we do need to be able to draw circuit diagrams, basic ones, like I've drawn here. I've got my battery, I've got my resistor. In this case, my light bulb is my resistor. In your booklets, this is the proper representation of a resistor. And the resistor, again, is important in our circuit because this is where the work is done. This is where the energy is converted to whatever the resistor might be. It could, like I said, it could be a light bulb, could be an element in a kettle. It could be your phone, whatever. Those sorts of things. Where is this chemical energy being converted? But this is another representation that you might see for a resistor. This is an older style diagram of a resistor, or if you're looking through some of the older booklets, or even in the more recent exams, sometimes they've slipped in this for a resistor. But you do need to know that they both represent resistors. And sometimes you might see a circuit represented like I've done, where the actual resistor